Alrighty, in this video we are going to talk about parametric equations and calculus. Now, hopefully you guys remember back in the previous video that the derivative of y with respect to t in terms of parametric equations is going to be dy dt over dx dt. Now, to find the second derivative, that's going to be very similar, but we are going to be using a little bit of the chain rule right here. So here, to find the second derivative, I'm going to say the derivative of dy dx. Now, if I'm taking the derivative of dy dx, it's just me saying the derivative of y with respect to x again. So if that's the case, then I'm going to have the derivative with respect to t of dy dx, because remember that dy dx is basically going to be in terms of t. But then dx dt doesn't really change, just because remember that we're taking the derivative with respect to y, which is going to be my numerator. So that's how I have d dt times dy dx over dx dt. So this is my second derivative right here. All right, this equation enables us to find the slope of dy dx of the tangent line at a point on the graph defined by parametric equations without having to eliminate the parameter t. The graph has a horizontal tangent line when dy dt is equal to 0, provided that dx dt is not equal to 0, and then the graph has a vertical tangent line when dx dt is equal to 0, provided that dy dt is not equal to 0. This should have been on the previous video. However, on the previous video, we were just talking about arc length. So this is now specifically for dy dx here. So here, if this is 0, then we are looking for horizontal tangent lines. And if dx dt is 0, then we are looking for vertical tangent lines. Okay, number 1. A curve C is defined by the parametric equations x is equal to t squared and y is equal to t cubed minus 3t. Part A says, show that C has two tangent lines at the point 3, 0 and find their equations. Well, in order to do that, I should probably figure out what t is. So to figure out t, I'm going to plug in 3 for x, or I could plug in 0 for y. Now, which one's easier, x3 or 0y? I'm thinking x being 3. So I have x is equal to t squared, 3 is equal to t squared, which means that t is going to be plus or minus root 3. Okay, so that's going to be my t value that I'm going to evaluate my derivative at. We want two tangent lines. So what I'm going to do is go ahead and figure out the equation of my tangent line by doing dy dx. And remember that dy dx is equal to dy dt over dx dt. All right, so the derivative of y with respect to t is going to be 3t squared minus 3. And then the derivative of dx dt is going to be tt. That gives me my derivative. Now, I have two values of t that I want to find. I want to find t is equal to what happens when t is equal to positive root 3, and then what happens whenever t is equal to negative root 3. If t is equal to positive root 3 right here, I'm going to plug in a positive root 3. And that's going to give me 3 right here. 3 times 3 is 9. 9 minus 3 is 6. 6 divided by 2 is going to be 3. So I have 3 over root 3. Keep it like that if you want to. That's fine by me. And then to find the tangent line, what you're going to do is, of course, do y minus 0. And then your slope of 3 over root 3, x minus 3. That's going to be your first tangent line. Now, if t is equal to negative root 3, we're going to be doing the same thing where we are plugging in a negative root 3 into my derivative. So then I get 3 since negative root 3 squared is 3. 3 times 3 is 9. 9 minus 3 is 6. 6 divided by 2 is 3. But then remember that I have a negative right here. So this right here, my slope at negative root 3 is going to be 3 over root 3, but make it negative. Your tangent line is going to be y minus 0, your slope, and then your x value. So this is going to be my 2 tangent lines. All right. Part B says, find the points on C where the tangent line is horizontal or vertical. Well, if my tangent line is horizontal, this is whenever dy dt is equal to 0. So that means that I'm going to set 3t squared minus 3 equal to 0. Solve for t. That's when t is equal to positive 1 or negative 1. Now, I am wanting to find points, aka rectangular coordinates. Since I want rectangular coordinates, what I'm going to do is go ahead and plug in a 1 here and 1 here so that I get my rectangular coordinate. So when t is equal to 1, this tells me that I have 1 square, which is just 1. If t is equal to 1 here, that's going to be 1 to the third. So 1 minus 3, or negative 2. When t is equal to negative 1, this is whenever I have negative 1 square, which is just going to be positive 1. And then if I have negative 1 right here, that's me saying negative 1 minus 3 times negative 1, negative 1 plus 3, or positive 2. So this tells me that I have a horizontal tangent line when my coordinates are 1, negative 2, and 1, 2. Now, my vertical tangent line is whenever I have dx dt being 0. So when dx dt is equal to 0, that is, let's see, 2t is equal to 0, so t is equal to 0. Well, if t is equal to 0, I'm just going to plug that in here, and I'm going to plug that in here, and that's just going to give me 0, 0. All right. Before I do part C, what I want to do is actually go to Desmos and show you the tangent lines, the horizontal tangent line and the vertical tangent line for 1A and 1B. What I'm going to do is go ahead and go to Desmos. This is just a demonstration. And I'm going to do, let's see, t squared, comma, t to the third power, let's see, minus 3t. And let's go from 0 to, let's say, 10, so that you can see what's happening here. Okay, so this is my parametric equation from 0 to 10. Now, negative 3, 0 is this point right here. So what I'm going to do is do y is equal to negative 3 over root 3 x minus 3. And then y is equal to 3 over root 3 x minus 3. Let's have that being, let's say, negative 10. Okay, there we go. So you can see here, I should have started at negative 10 to 10, because technically t doesn't have to be 0. So notice how here, my parametric equation, my graph, my curve looks like this. And notice how, like number 1a said, we have 2 tangent lines. the negative tangent line right there, and then the positive tangent line right here at 3, 0. So that was 1A. 1B told me find the point on C where the tangent line is horizontal or vertical. So if I have, let's say, 1 comma negative 2, that's right there, and 1 comma 2, that's right there. So that tells me that my horizontal tangent line is going to be y is equal to 2 and y is equal to negative 2. You could also see that at 0, 0, that I'm going to have a vertical tangent line right here at 0, 0. So my green and purple lines tells me part A, and then my red dot, my blue dot, and my black dot represents part B, where we have my coordinates where my tangent line is either horizontal or vertical. So that's just a little representation for you in terms of 1A and 1B. Part C says determine where the curve is concave up or concave down. So that means that I'm going to be using my second derivative, aka this lovely thing right here. Well, I know what dy dx is because that is this lovely thing right here that I just found. So I'm going to have the derivative with respect to t of dy dx. In this case, it's going to be 3t squared minus 3 over 2t all over dx dt. And that's going to be 2t. I'm going to simplify this before I take the derivative. So d dt is going to be equal to 3 over 2t minus 3 over 2t over 2t. So then if I take the derivative, that's going to be 3 halves. And let's see, plus 3 over 2t squared over 2t. Now, we want to determine where the curve is concave up or concave down, so that means that we're going to be setting this equal to 0 and seeing what happens here. I am going to make this a little bit prettier, so I'm going to simplify this so that I have 2t squared. So 3t squared over 2t squared plus 3 over 2t squared. So now I have 3t squared plus 2 over 2t squared all over 2t. And then if I same change flip that, I'm going to get 3t squared plus 2 all over 4t to the third. And I'm going to set that, that should not be 2, that should be 3, huh? All over 4t to the third power. All right, so once I do that, I'm going to set this equal to 0, since I want to find my concavity here. In that case, when this is 0, this is when, let's say, t is equal to 0. So that's my only little critical point. If I were to substitute in a negative number right here, this is going to become positive no matter what, because this is positive and this is positive. But my numerator right here, since I have a negative value right here, a negative times a negative and a negative will be negative. And then if I were to plug in a positive number here, that's always going to be positive. So this is positive. So this tells me that I am concaving down from negative infinity to 0. And then I'm concaving up. Oops, not down. Up from 0 to infinity. Now, this is going to be very important. Remember that this is in terms of t. All right. So if I were to look at this right here, where I'm going from negative infinity to 0 and I'm concaving down, well, if I have that, and then let's say that this is 0, notice how my graph concaves down, my curve. And then if I were to do from 0 to, let's say, infinity, or in this case, let's say 10, you'll notice that my graph kind of concaves up. So it concaves down from negative infinity to 0, and then here it concaves up from 0 to infinity. All right, so that was just number 1. Number 2, so let's write the equation of the tangent line at t is equal to -1 for the parametric equations x is equal to 1 over t and y is equal to t. Well, we kind of need to figure out what the coordinates are at t is equal to -1. So what I'm going to do is, of course, just plug in -1 for x and y to get my rectangular coordinate. And if I were to plug in -1, that's going to be -1 over 1, which is just -1. And if this is t and t is -1, then I'm also going to get -1. So that's my point, my first step. My second step is going to be finding the derivative. So that's going to be dy dx. And remember, that's going to be the same thing as dy dt over dx dt. In this case, dy dt is just going to be 1. Dx dt is going to be 1 over t squared. And if I'm plugging in -1 right here, this tells me that my slope is going to be 1. Oh, sorry, -1. Sorry, the derivative of 1 over t is -1 over t squared. So that's going to give me -1 right here. All right, so my equation of the line at t is equal to -1 is going to be y plus 1 is equal to -1 x plus 1. Number 3, we want to write the equation of the tangent line at t is equal to pi over 4 for the parametric equations x is equal to sine of t and y is equal to cosine of t. And remember that this is a circle with a radius of 1. All right, to find the equation of the tangent line at t is equal to pi over 4, I'm going to go ahead and take the derivative. So that's going to give me, let's see, negative sine of t, then cosine of t, which is negative tangent of t. Well, if t is pi over 4, I'm going to have negative tangent of pi over 4, and that's just going to be -1. So that's going to be my slope. Well, we have my slope, so that's great. I need to figure out what my rectangular coordinate is. So I'm going to plug in pi over 4 here and pi over 4 here. Lucky for us, they're just the same value. It's just root 2 over 2 and root 2 over 2. So now I have to write my tangent line equation. Y minus root 2 over 2 is equal to -1, x minus root 2 over 2. Of course, I'm going to show that to you guys for number 3 so that you can see that that is the tangent line at pi over 4. Oops, not that one. So here, if I have x squared plus y squared is equal to 1, and we have pi over 4, then I have y minus, let's see, root 2 over 2 is equal to -1 x minus root 2 over 2. And you can see that this is root 2 over 2, and that gives us that tangent line right there. Pretty cool. Number 4 says find any horizontal and vertical tangents for the parametric equations x is equal to t squared minus t plus 2 and y is equal to t to the third minus 3t. All right, so once again, we want to find tangents, so we are going to be taking the derivative separately. In this case, remember, if I want horizontal tangents, this means that I am going to be taking the derivative of y with respect to t. That's going to be 3t squared minus 3. I'm going to set that equal to 0. And that means that I have t being, 3t squared. 1 is equal to t squared. So t being plus or minus 1. And all you're going to do, of course, is just plug that into x and y. In this case, for time, you're going to get 4, 2, and 2, negative 2. For 4, 2, that's you plugging in t is equal to negative 1. And then for 2, negative 2, you're going to plug that in for 1. You're going to do the same thing for vertical. So that is when dxt is equal to 0. So that's 2t minus 1 is equal to 0. T is equal to 1/2. And then for time's sake, I'm just going to tell you that if t is 1/2, then my rectangular coordinate is going to be 7/4, then negative 11/8. All right. Number 6. Suppose that a curve C is described by the parametric equations x is equal to f of t and y is equal to g of t for all t is greater than 1. And we have this lovely thing right here. That looks like a mess. And then it says, what's the value of dy dx when t is equal to 3? Well, notice how you have the derivative of y with respect to t, and then you have the derivative of x with respect to t. I'm going to divide that, so dy dt over dx dt. And that right here just becomes, plot twist, dy dx. And if I want to find the derivative of that when t is equal to 3, I'm just going to plug in 3 and call it a day. So that's going to give me 10/2 or 5. Crazy, I know. All right, let's go ahead and do number 8. A curve C is defined by the parametric equations x is equal to 1/2 t squared plus 2, y is equal to t squared plus 2t plus 4. Find the equation of the tangent to C and determine the concavity at t is equal to 2. Okay, so we are looking at when t is equal to 2. So what I'm going to do first, of course, is figure out what that is in terms of my rectangular coordinate. I'm going to plug in 2 here, here, and here. So x is going to be 1/2 2 squared, 1/2 4, and that's going to be 2. Y is going to be 2 squared plus 2 times 2 plus 4, which is equal to 4 plus 4 plus 4, or 12. So this means that my rectangular coordinate, oh, I forgot the plus 2 here. So plus 2, plus 2, plus 2, so 4. This means that my rectangular coordinate is going to be 4, 12. All right, now we got to find the derivative. So to find my derivative, once again, we have dy dx, dy dt over dx dt. In this case, dy dt is 2t plus 2. Dx dt is just t. I'm going to plug in when t is equal to 2. So that's going to be 4 plus 2, 6. 6/2 is 3, which tells me that my slope at t is equal to 2 is going to be 3. Okay, so now just write the equation of the tangent line. Y minus 12 is equal to 3x minus 4. That's going to be your equation of the tangent line. Nice. It also says determine the concavity at t is equal to 2. So I am going to be taking the second derivative. Remember that the second derivative just means that I'm going to be taking the dy dx with respect to t. In this case, I already know that that's going to be 2t plus 2 over t. I'm actually going to clean that up a little bit. That's 2 plus 2 over t over dx dt, which is just t. The derivative of d dt of 2 plus 2 over t is going to be negative 2 over t squared over t, or the same thing as negative 2 over t to the third power. And if we set that t is equal to 2, then this is me saying 2 over 2 to the third, which is 8. And I'm going to get negative 1/4. Okay. Now remember that we have a negative 1/4, and because my second derivative is negative, this tells me that my concavity at t is equal to 2 means that I'm concaving down at t is equal to 2. What I'm going to do, again, is show you visually what's happening here at t is equal to 2. So here I have 1/2 t squared plus 2. And then I have t squared plus 2t plus 4. And we want to see what's happening at t is equal to positive 2. Okay, that's this thing right here. So when t is equal to 2, that is 412. So I'm going to go ahead and graph that so that you could visually see where that is. 412. That points right here. Now my tangent line equation was y minus 12 is equal to 3x minus 4. So that works out. Then you could see that here that it kind of just concaves down when t is equal to 2. So here's what's happening at 2. Let's say 2.2 is right there, 2.3, 2.5, and so forth. So we're kind of concaving down at t is equal to 2. All right, the other problems are going to be self-explanatory. They're very similar. All we're doing here in this lesson is determining horizontal tangent lines, vertical tangent lines, concavity, and then, of course, just dealing with your derivatives. Nothing too big here. In the next video, we are going to be talking about vector value functions and how that's going to help us with parametric equations. See you then.